So let's do some examples of degraded channels. I will start with the binary channel. So this is sometimes called the binary symmetric broadcast channel. And the idea is it's like the Gaussian channel. So we have so everything's binary. All alphabets are binary. And we get x, and we'll have x or z1. y2 is x or z2. And what we are saying, z1 is Bernoulli, let's say p1, and z2 is Bernoulli p2. And let's say let's say 0 less than p1 less than or equal to p2 less than or equal to half, just so that we don't have to worry about going above a half, which will make the notation complicated and doesn't give us any extra insight anyway. Okay, so is this channel degraded? It's the first question, and the answer is yes, because I can come up with a different y2, let's just call it y2 tilde, which is y1 x or z, let's just call it 1, 2, where z12 is Bernoulli p2 minus p1. I have to be careful if I'm doing this right. I have to be careful. So, well, what is the parameter going to be? Let's try to figure out what that is. p12. There is such a parameter, because what I have is, if you think about what's going on, what I have is a z parameter where, so because this thing here is going to be then x or z1, x or z12, right? And I need to have the statistics, the crossover of this, to be the same as the crossover statistics of z2. So if I start with z1, I would have 0, 1, right? The first crossover probability to get to I already have z1, and then I'm going to x or z12, so this is the crossover p12, so this will be 1 minus p12, this will be p12, 1 minus p12, 0, 1, and what I want to have here is that this is y1 and this is z1 and this is this here is z2, right, or y1 and y2. But if I start with z1, I know that 0 is, I get 0 with probability 1 minus p1. I get 1 with probability p1, and here I want to have this to be 1 minus p2, and I want to have this to be p2, right? That's what I want to get, right? So, well, I think you know that works, but we can see what the equations are. Well, now it's we can write 1 minus p2 is 1 minus p1 times 1 minus p2 plus p1 times p12. This should have been 1, 2, sorry. And then I have to solve this equation for p12, right? So plus, let's just do this. 1 minus p1 minus p12 minus 2p1 p12. So I collect these two together. 1 minus p1 minus p12 times 1 minus 2p1. And so I get p12 is equal to, if I did everything right, 1 minus p2 minus 1 plus p1, so I get p1 minus p2. So the 1's cancel, p1 divided by 1 minus 2p1. Right? And okay, this is positive, and hopefully this here, well, this here is going to be positive too, and hopefully this fraction is less than 1/2. But anyway, that's the solution, right? So I'm pretty sure it looks right, the general expression. I don't know if it's perfect, but anyway, so that's plus 2, where? Oh, where? Oh, plus. Yeah, plus. Oh, sorry, plus, thank you. Plus. Well, now I'm even happier because that'll definitely be a small number, right? Good, so thank you. so that we can find one so that the marginal statistics are the same, right? Because for the marginal statistics, we don't have to worry about the cross correlation. Okay, so as long as the crossover probability is the same, we get the same statistics. So indeed, this thing here is stochastically degraded. Or the usual language, again, is just to say this is degraded. So there is another channel that's physically degraded that has the same marginals as the original channel. Okay, because of that, we know what the capacity region is. There it is, right? So we've shown this is the capacity region. So let's compute this capacity region. Let's compute this capacity region. Okay, so we can just keep the original thing. So fine, so now we have to choose u's. It turns out, I should say, for these problems, we can show that u is at most x, which is a good thing for these problems, because that means we can choose a binary u. Moreover, so what we'd have to choose now, so possible choices, pu x given u, right? Since we know u is binary, we may as well start with 0 and 1. And then we'll have x, 0, 1, right? And we have to choose some channel, right? Let's call this 1 minus q0, q0. You know, the channel might have to be asymmetric, right? In general, we have to look at the complete freedom. This is going to be x1. And then we'll get, we may as well look at the degraded version. So this will be x, this will be y1, and this one will be y2. If we want, we can look at it from that perspective, where this was the crossover p12, and this was 1 minus p1, right? Now, it turns out you can prove that the optimal choice of channel here is symmetric, and that's done by something called Mrs. Gerber's lemma. That's one way to prove this. Of course, you could just do it numerically, but you know, some people, if you're a mathematician, you might not be happy with numerics because you only can show things to the 64th digit or something, right? So maybe in the 65th digit something happens, right? So to do a proper proof, you need some theory. Of course, an engineer would say, who cares, right? But sometimes, you know, if you want a perfectly exact answer, you need some theorems. So Mrs. Gerber's lemma is a little bit like the entropy power inequality. But anyway, so what we'll do is we'll just restrict attention to channels px given u that are binary symmetric channels. It turns out that's optimal, and one can prove that. But it's not obvious ahead of time. So, okay, so we choose a BSC. So the channel we'll choose it is Q, right? So what we'll do is we'll say X is U, X or ZU, where ZU is Bernoulli Q. However, what will be important is that U won't be uniformly distributed. And even in that example I just showed, it wasn't clear that so there were more parameters. There was the probability of U is 0 and 1, and also the asymmetric crossover. So there were actually 3 parameters to optimize over. The probability whether U is 0 or 1, and the probability of the 2 asymmetric parameters. Now we're saying, well, we're going to just choose 2 parameters, Q, and also we need to design the distribution of U as well. Actually, is that right? I take that back. It's this here was Q, so it turns out I take it back. U is actually Bernoulli half. That's what we'll choose. It'll turn out that this choice is optimal. I take it back. So, but in general, we would have to test all 3 probabilities, right, in our optimization. And then we somehow need to prove that this choice is good enough. It turns out this choice is good enough. So what we're getting effectively then is, if we, well, let's now compute these mutual informations. We can start with this one. So let's compute I. It's also the same kind. I of, this one's a little better. I of U, Y2. Okay, let's check what is that. Well, that's H of Y2. minus h of y2 given u2, given u. And what is y2 though? y2 is x XOR z2, and x is u XOR zu. So this is the entropy of u XOR zu XOR z2 minus h of u XOR zu XOR z2 given u. Okay? Okay, so what's the, this is our binary random variable. What's its distribution? This is Bernoulli half, this is Bernoulli q, this is Bernoulli p2, so this is half, right? Because the half makes everything uniform. So this is just 1. What about this one? Well, here, the first thing we notice, because we have the condition we can XOR it out. This is h of zu x XOR z2 given u, but these two are independent of u, so this is the same thing as if I just had this. Okay, so what is the probability of 0 and 1 here? Well, we can just compute this. So, and usually there's a notation used for that. So if we have, for example, we just did it actually before. So suppose here we have, well, the probability of z u XOR z2 of 0 is going to be the probability that this is 0 times the probability this is 0 plus the probability that this is 1 times the probability this is 1. So then it will just be p, well, this here is q, right? So it's 1 minus q, 1 minus p2 plus q p2. And for the probability of 1, and that's the one I want to focus on, of 1, well, both are important. So we'll get probability of this times p2 plus q 1 minus p2, right? And this is sometimes called q star p2. Okay, that's just by definition. Now, if you look at this, what does star remind you of? Convolution. Is there a convolution going on here? Turns out the answer is yes. Yes, there actually is, and this is quite important because convolutions, we know if we take Fourier transforms of some kind, we get products, which can be helpful, but let's just do. So what is the convolution that one is thinking of? What one is thinking of is two vectors. The first vector is 1 minus qq. The second vector is 1 minus p2p. And suppose I take the convolution of these two vectors cyclically, the cyclic convolution, well then I just get these two numbers, right? So in fact, you know, this really is it is one of the parameters of the convolution, and that's actually important for implementing non-binary low-density parity check codes, because it turns out for non-binary low-density parity check codes you have like a parity check with like A, B, C, and to compute like the log likelihood ratios for problems like this, you wind up writing out sums like this, and then you can show that the values you need for your probability distribution you can compute as a convolution, just like here. And if you're using, say, Galois field of size 64, then you would have an 8-bit convolution, and you can do the convolution quickly using a fast Fourier transform, and then take products and inverse Fourier transform. That's a lot faster than the quadratic. It's not complexity 64 squared, but you know, n log n times 2, you know, times the product. So you get a linear n log n style of complexity. And especially once the finite fields grow to like GF256, you save a lot of processing power. So it's just interesting to keep in mind that operations like this, the convolution, there is a kind of convolution going on, and it's a very important observation practically too. So when you implement some very, and non-binary low-density parity check codes are really good at short block lengths. So they're one of the best classes of codes for short block lengths. Anyway, that's just in case you're interested in that sort of stuff. But anyway, we'll call this q star p2. So this is nothing other than the binary entropy function of q star p2. Right? So let's just write that. That's why I just wrote it like that. Okay, so that is the first mutual information. So let's write that out. So I uy2 is h2 q star p2, because remember we still can optimize over q, right? So we'll do that in a moment. Okay, so let's do the second mutual information. Okay, what about I of x, y, 1 given u? Well, that is the entropy of y1 given u minus the entropy of y1 given x and u, but that's just y1 given x. Well, now we just do the same thing. y1 is x XOR z1, but x is u XOR zu XOR z1 given u minus h of, well, what's h y1 given x? That's just h2 of p1. And this here we can again drop the u, and here, so here we'll get h2 of q star p1 minus h2 p1, right? So it's the same thing, just slightly different. So this here is going to be the rate that we can achieve for user R0 plus R2. And this is the rate we can achieve for 1. It's going to be h of, oh, I forgot. What did I do here? 1 minus this, my apologies. 1 minus h2 q star p2, h2 q star p1 minus h2 of p1. Right? That's the region. So that defines my rectangles. And now let's look at what happens with these rectangles as we vary over q. Okay, so we'll now vary q and look at what happens to the rectangles. All right, so let's try it. R0 plus R2, R1. Okay, first of all, suppose, so what can I vary q as? Well, q goes from 0 to a half, right? So what happens when q is 0? Suppose we start with q equals 0. Well, what happens, what's q star p2 when q is 0? So remember, q star p2 was 1 minus q p2 plus q1 minus p2. So if q is 0, all I'm going to get is p2. So this is just 1 minus h2 p2. Okay, so that's this. And what is this? Well, that's just p1. So we get h2 p1 minus h2 p1 is 0. Ah, so q equals 0 means we're operating at this point. Is that a good point to operate at? 1 minus the binary function of p2? Well, sort of. It means we're not sending any information to user 1, right? And you can't do better than this, because that's the capacity of the channel to user 2 if you weren't sending information to user 1, right? So this is optimal. That's on the boundary. The same if we go to q is a half. What happens if q is a half? Q star p2 is just a half times p2 plus a half times 1 minus p2 is a half. So this is just 1. So we get 0 here, and here we'll get 1 minus h2 p1. Also optimal. So this here is q equals 0, and this here is q is a half. And you can imagine that if you go in between, you'll get some rectangles that look like this. So we can maybe do an example. Suppose we choose q so that this number is a half. Well, that's going to still be tough because I'm getting something funny. It's hard to draw. Anyway, so if we did draw it, because it depends on p1, p2, you're going to get a curve that looks like this. It comes out with slope 0 and then comes in with slope 1. And all these points are just the union of the rectangle values, right? So this rectangle might be, you know, q is 0.1, this q might be q equals 0.2, this might be q equals 0.3, and this might be q equals 0.4, right? Just as an example, right? And so you're just drawing out the, you know, this, you're just tracing out where those boundary points are behaving. And that is the capacity region of this binary symmetric broadcast channel. it turns out that's the optimal choice. If you choose any other statistics, we could have chosen U to be non-uniform, and we could have chosen the channel to be asymmetric, but you can prove that this is optimal. One way of proving that is using the so-called Mrs. Gerber's lemma that Weiner and Ziv came up with in 1970 something, 2 or 3. So they proved this. It was actually, this channel has an interesting history. This capacity region was first found by Bob Gallagher. So Tom Cover came up with his broadcast channel paper. I think that caused a lot of interest from the community to look at these channels. Bob Gallagher wrote a paper in the Problemi Peridaci Informazi. That was the Russian journal that had a lot of information theory in it. Very beautiful paper, you know, typical Gallagher, where he basically did the converse I showed you, appeared in that paper. I think it was the first paper that really developed a converse with these auxiliary random variables. Then he also showed, you know, how to optimize this. He also showed what he found the cardinality bound on the auxiliary random variable, that it's at most x. And so it's a rather rich paper. Like, and at the time it was brand new. I mean, it was, and he also has error exponents that he derived for the broadcast channel there too. So he was doing maximum likelihood decoding rather than typical sequence decoding, and he developed error exponents also. I think it's in that paper. I'm pretty sure he did. And then, so that found the capacitor region, but of course you still have to optimize it. And Weiner and Ziv found this special inequality. They were interested in it for a variety of reasons, and then they applied it to this problem and were able to show that the optimal choice of distribution to get the capacitor region boundary has the symmetric form, that U is uniform and that the channel is a binary symmetric channel, right? That's a simplification on the original result. Then let's look at the Gaussian channel, and now we'll start working with the Gaussian channel a little bit. So we've already talked about it somewhat. I think this channel is a little bit easier to talk about. In particular, if I just focus just quickly still on this example, binary symmetric channel, note that how, like, the PU x given U channel was a binary symmetric channel with crossover probability Q, which isn't a half. Now there's something bad about that, and what it is that this is not uniform. And when we use linear codes, we like to have, you know, half-half, because if you use a linear code, the probability of 0 and 1 is equal. So as soon as we get anything asymmetric appearing, we need to do shaping. So we need to make the probability of 0 be 1 minus q and the probability of 1 be q. And that's not so easy to design. Like, you have to go beyond linear codes now. You have to do something different. So it's not so obvious. For these channels, that is a complication that already starts appearing. Even though the channels are both symmetric, we have to build something asymmetric to get the best possible rates. But anyway, let's talk about the additive white Gaussian noise channel. This is the one that interests us the most, is the most practically interesting. So we already talked about that. We have x plus z1, y2 is x plus z2. So this is the scalar case that we'll first talk about. This thing here is 0 mean, let's say sigma 1 squared. This one here is 0 mean sigma 2 squared, and we'll do the same degraded ordering. Sigma 1 squared is less than sigma 2 squared. Okay, so the signal to noise ratio, and we'll have a power constraint, of course. The summation from I equals 1 to n of the expectation of x I squared divided by n has to be less than p. Or if you want to have a probability 1 power constraint, you would remove the expectation, but the capacity regions are the same for large n anyway because of the law of large numbers. So, well, whatever, right? So just power constraint, the usual power constraint. All right, is this channel degraded? Well, we said yes, because we can come up with another channel where this is just y1 plus z 1, 2, where this here it's clear. This is 0 mean with variance sigma 2 squared minus sigma 1 squared. right? And then the marginals are the same. Like here I can just subtract the variances, right? So clearly this channel is stochastically degraded. It's not necessarily physically degraded unless there's some special correlation between these two. But it definitely is degraded, and because it's degraded, we know this is the capacity region. So let's try to compute this region, and then we can again plot curves like this. That's what we'll start doing. Just repeat this whole analysis now just with Gaussian channels. Okay, we need to choose a channel PUX. Of course, for Gaussian channels, there's only one natural choice. Namely, we'll choose x equals u plus v, where this thing here is zero mean Gaussian with power, let's just say alpha p, and this thing is zero mean Gaussian with power 1 minus alpha p, or the other way around. Let me do it so that I do it right. Yeah, 1 minus alpha p, the same way. Okay, where alpha varies between 0 and 1. Okay, and if you look at this structure, you already sort of see how a different kind of coding method, right? One code word for u, one code word for v. But here, remember, our coding structure is different than that. Our coding structure isn't. So this here, this kind of form motivates doing the following. Taking messages w naught, okay, one of them will decode, u will decode at both, right? So that corresponds to r naught, r2. So we'll take the two messages, these bits, concatenate them and code them into u, un, and then choosing a separate encoder, putting this message in, generating a v, and then just adding the two up, right? This is multi-stage decoding version of superposition coding, right? That's natural. That's not how we built up our codebook, though. We built up our codebook by stacking, remember? So it's different than this. In fact, we didn't have a separate encoder, we encoded w directly into x from this. So we had, we took this and added w1 and then put it directly into x and w naught w1. That's what we sent, right? Encoder. In other words, this code book never existed, right? Effectively, w1, w2. Right? That's how we actually did it. And formally, the code structure is different for both, in fact. But the way most people think of superposition coding is what I just drew. And of course, that is a simple way to implement it. But it's interesting to think whether the other design doesn't sometimes have some advantages or disadvantages. Right? Most people do superposition coding this way because it's easier to understand. But again, it's a different design than the way we did it. Okay, just keep that in mind. It's a different architecture for the encoding. And it turns out actually for some problems doing it this way doesn't work as well as doing it the stacking way. And that tells you something. It tells you that designing codes in different ways, actually does make a difference in what the performance is. So, okay, so that's not how. So we're not going to look at that more. I just pointed out to you there's different architectures. We're just interested in doing this to evaluate this region, right? That's it. So let's do that. Okay, so let's compute this. Is that clear what I said? I hope. Okay, let's do this. IUY2 is the differential. Everything's Gaussian, so we have to have continuous random variables. So let's look at the differential entropies here. This here is H. So what's Y2? It's X plus Z2, but X is U plus V, so we get U plus V plus Z2 minus H of U plus V plus Z2 given U. Oh, and all these are independent, right? Independent, of course. So here I can subtract out the u, h of v plus z2 given u, but that's just equal to h of v plus z2, right? Because the u and the v and the z2 are all statistically independent. So what do I get? I get that my rate r0 plus r2 is going to be, well, it's going to be, well, what is this? Well, I guess I could have just kept this as x plus z2. And then what's the entropy of this? It's a Gaussian random variable with the variance of p plus sigma 2 squared, right? So what we'll get is, this is 1/2 log 2 pi e p plus sigma 2 squared, right? This here is 1/2 log of 2 pi e of v plus c2, but v has power 1 minus alpha p, so it's 1 minus alpha p plus sigma 2 squared. Right, so I get this divided by that, so I'm just going to get 1/2 log 1 plus alpha p over 1 minus alpha p plus sigma 2 squared. Right? That is my equation. So I get a signal to noise ratio. It should sort of make sense. U is like my channel I'm sending. V is like noise now. So the noise signal, the interference plus noise has power 1 minus alpha p plus the noise at the receiver, and this is my transmit power in U. So this is just a signal to interference plus noise ratio, where the interference is caused by the transmitter. Right? So this is just the SINR of receiver 1. Similarly, receiver 2, well, if you look at it, if we go to this expression, U is cancelled. So I'm getting rid of U, otherwise I have a noise-free, I just have channel with noise, but let's just write it out formally. So we'll just get another signal to noise ratio now. There's going to be no interference because the conditioning removes the interference. Right, this is just the noise. This here is h of, well, y1. I can remove the u's because it's u plus v plus c1, but I can remove the u, so I get v plus c1. And so this is just going to be 1/2 log, well, let's write it, log of 2 pi e. Okay, this is 1 minus alpha p plus sigma 1 squared minus 1/2 log 2 pi e sigma 1 squared. And so I also again get the signal to noise ratio, again log of 1 plus 1 minus alpha p by sigma 1 squared. Okay, so that's my region, and I can now still take the union of all such regions when I optimize, when I vary alpha from 0 to 1. Okay, so let's do that. And then we'll draw again another region, so same thing, same idea. Okay, so let's start with alpha equals, well, we can start with 0. Fine, start with alpha equals 0. If alpha equals 0, here we get 0, so we'll get 0 r0 plus r2, and we'll get 1 plus p over sigma 1 squared, right? 1/2 log of 1 plus p over sigma 1 squared. Does that make sense? Well, yes, that's just the capacity of the channel from the transmitter to the first receiver, right? And I can't do better than that for rate 1. That's alpha equals 0. What about alpha equals 1? Well, if alpha equals 1, this goes to 0, right? So that rate is 0, and here I'm going to get 1 plus p divided by sigma squared. So I get the same kind of answer, but this number is smaller because the noise is stronger, right? 1/2 log 1 plus p by sigma 2 squared. Okay, and as I vary alpha, I'm going to get the same thing. What you'll notice is that the slope is 0 here, and the slope here is 1. Okay, and that has, that's an important just observation here. The slope is 1 here at 0. And effectively, again, this is just a union of such values. So this here is alpha equals 1, and maybe this here is alpha equals a half. So all you're doing is, as I sweep over alpha, I get the boundary of this curve, and you can prove that Gaussian channel, a Gaussian channel and a Gaussian U are optimal, and this can be proved using the Shannon's entropy power inequality. Okay, so Tom Cover had this in his paper. Bergman's, one of his PhD students, then found that the entropy power inequality could prove the converse. Bergman's extended it to many receivers where you have a degradation. So for example, suppose we have a 3-user broadcast channel, 4-user broadcast channel. It turns out the optimal region is always done by using superposition coding with more levels as before. Okay. Any questions about that?
So any limit on the number of levels?
Well, you can choose as many as you want, but here you only need 2, right? So if you have a scalar Gaussian channel with many receivers, you'd need as many levels as receivers. Yeah. So and that's also a new compound channel. So suppose we have 3 channels. It's like having a compound channel with 3 subchannels, and then in case one channel occurs, you can decode the first layer. If the better channel occurs, you can decode maybe the first and second layer. If the best channel occurs, you can decode all 3 layers. That's useful for things like video coding, right? Because then you're just decoding as much as you can, and yeah, then you show the video at a quality level depending on whatever the quality of the channel is, even though a better receiver will be able to code all 3, right? So that's the way you can do multicast too at different quality levels. Right, so that's what's done actually, in practice. Although it's not done using superposition coding. Usually, it's done using some more time, a little bit of a different approach. Maybe you can view it maybe as superposition coding. I don't know. Any other questions? Okay, but maybe we should continue on this track. What's another method we could use? And we should think, right? I mean, doing this kind of superposition coding takes a little bit more processing. So maybe what's the more natural way to do broadcasting? It's time sharing, right? So we send some time only to receiver 1, and we send the other time only to receiver 2, right? So we can think about doing that and then plotting what kind of rates we get. In fact, what kind of rates would we get if we just sent at power p part of the time to transmitter 1? We would be operating here. And sending the other part of the time to receiver 2, well, you would be just getting a line in between. So let's draw that, because this is going to be a little bit interesting. So time sharing, pure time sharing, by splitting the time or frequency resources into 2 sets, would give us points on the blue line, right? So this motivates using superposition coding. Aha, says someone, but I can do better time sharing than this. Is there a better way of doing time sharing than just operating between these 2 points? And the answer is yes. It turns out what I can do is the following trick. And this probably was what someone pointed out at the beginning, right at the very early years, because it wasn't yet clear whether this kind of stuff was useful at all, right? So what's another strategy I could use that uses orthogonal signaling? In other words, no superposition, not sending to both receivers at the same time. Well, let's send at the same time but in different frequencies, right? So I can do that. Or maybe I can do something else. Maybe I can do the following. Let's divide time into 2 pieces. Let's say, I'll use the same. No, let's use a different letter. Let's say beta of the time I use mode 1 minus beta of the time I use mode 2. But in mode 1, I'm going to send with power gamma p, and in mode 2, I'll send with power gamma 2p, and I just want to make sure that gamma 1, that the overall average power matches, right? So what do I need here? So how much power am I using here? Well, beta, well, the power I'm using this time is gamma p1, but what I need is that gamma 1 beta p, gamma 1 beta p plus gamma 2 1 minus beta p has to equal p, right? That's so, and I can optimize over my gamma 1 and gamma 2 and beta, right? So I still have some room to play. So I'm not always sending with the same power. Okay, and it turns out if you do that, and I didn't quite explain it in the simplest way here, but if you get the idea, right? I can change powers over different times. You actually improve the rates. You actually get rates that look like this. Okay? Which is interesting, because this method is still very simple. It's pure orthogonal signaling with just different power levels and different times. And optimizing the time and optimizing the powers. Okay? So it's important to keep those things in mind. Doing orthogonal signaling, you do have more opportunity to work if we're having a block power constraint. Now, of course, if the power constraint was per symbol, I couldn't do this, because then I'd have to send it always at the same level, and then I'm limited to the blue curve. But if I have a block power constraint, you have actually more freedom to try out things. And amazingly enough, here you actually do better. But you still don't do as good as superposition coding. So there's a paper by Bergmans and Cover called Frequency Division, something like this, where they have a plot. You know, they just plotted this to point out they're actually doing better than any orthogonal signaling method. Okay, but still, I think it's useful to keep this in mind even for real systems, because you may not want to build superposition coding anyway, just out of complexity reasons, so you can still do orthogonal signaling and do better. Okay, we'll see something similar happening for multiple access channels. Something similar will pop up there too, just with a little bit more of a surprise, a little bit more sophisticated thing. So that's the scalar broadcast channel. Now what I want to do, let's see here, I still have a bit of time, right? So there's two things I'd still like to do with Gaussian channels, so we're just going to stick to Gaussian channels. That'll finish the broadcast channel section. One is Martin coding, and the second is vector broadcast channels. Okay, so let me begin with Martin coding. Well, here we used superposition coding. What about Martin coding, or you know, the binning method with Gelfand-Pinsker rates? Suppose we did that here too. So instead of using superposition coding, we can use something else. We can use Martin coding, and let's see if how good rates we get. Okay, so suppose we use Martin coding. Remember what the rates were? What were the rates? Well, we had this funny looking region, right? Right? But let's just go for the corner point that we talked about, and with the Gelfand-Pinsker design where we get rid of interference. So the rate looked like this, right? There was rate naught plus rate 2 was the same as up here, IU, I2. And rate 1 was given by what? It was I have to think that this was IU2, Y2. This was IU1, Y1 minus IU1, U2, right? That was the choice, right? And now we can choose what we would and we're viewing U2 as like interference for like state. And remember, for Gelfand-Pinsker coding for Gaussian channels, we made special choices of parameters to get rid of the interference. We can do that too, so let me just write out what those parameters are. So what we'll do is choose the following. U2 is 0 mean alpha p Gaussian. Of course, that has to be the same. That's the same, so that we get the same rate here. Okay, so that'll turn out to give the same rate here. We want this term to be the same, so we're going to use U. The U2 is like the U we used before. We're going to choose a U1, I should say it this way, X1 to be 0 mean 1 minus alpha p. So this is like my V. Maybe I can call it even a V. We'll call it a V. Well, let me call it x1 just because that's why I drew it that way in the graph. I want the relationship to the Gelfand-Pinsker problem. Then we'll choose u1 to be x 1 plus beta u2, right? You'll remember this was the state. When we looked at Gelfand-Pinsker, we had x plus beta times the state. So that's the state. This is my x. And then we'll choose x to be x1 plus u2. That's what we're transmitting. And if you put that all together, you'll get exactly these rate expressions popping out at you. Where the, oh, and beta, I have to choose beta. Beta is the signal to noise, is p over p plus n. And here p over p plus n is 1 minus alpha p over 1 minus alpha p plus sigma 1 squared. So that's the same, that's, remember for our parameter alpha, this was x1 plus alpha state, and alpha was p over p plus n. Here the p is just the 1 minus alpha p because we're just corresponding to the power of u1, which is, well, this x1, this 1 minus alpha p, that's why. And if you put that all together, you'll get exactly this rate region where we've removed all the interference from u2 here, and here we'll have to live with the interference from the other term. Okay, and then so you get the exact same region. So this is interesting for Gaussian channels. For Gaussian channels, I can choose to do either superposition coding or Martin coding, but usually I choose superposition coding because it's kind of hard to implement this Gelfand-Pinsker coding scheme. It's much easier just to generate one code word U, another code word V, and add them up, right? I mean, from an implementation perspective, that's way simpler. Superposition coding is always easy to implement like that, just adding up two terms, okay? Questions about that? Now, for the binary symmetric broadcast channel, though, using Martin coding won't give you the full region. So that shows you, tells you that in general, we need both. We need both superposition coding and Martin coding. You can't leave one out and still hope to get the best performance because there are degraded broadcast channels for which Martin coding is suboptimal, like binary symmetric broadcast channel. Okay, so this brings me to the final topic on broadcast channels. I do want to say a few words about the vector broadcast channel.
Can you avoid using blue?
Yeah, I see that.
It's not visible and
I
suspect
the camera,
nothing is
probably visible here, yeah, but it's in the course notes. But yeah, I'll avoid. I will redo this now anyway for vector channels. So that way you'll be able to see it, and you'll just have to specialize it then down to the scalar case. It'll be more complicated. So let me go to the vector broadcast channel. So the vector case, for the vector case, let's look at the channel model first. So we're going away now from degraded channels. So that's the first unfortunate thing. So we have to say goodbye to this region. There it goes. I shouldn't say goodbye to the bound. That's a physical limitation. Right? So let's look at the vector case. So this is the case that got a lot of interest about 15 years ago for very practical reasons, because most companies, large companies at that time, Lucent, Alcatel, Ericsson, Nokia, Huawei, all built base stations, and these were their large margin products. Cell phones usually have low margins, and most of these companies weren't into cell phones or had sold that part already, right? Huawei built cell phones too, but Alcatel-Lucent does not, and so on. So that business was very changed in a much different way than the base station business. So in base stations you have a lot of transmit antennas. So our new channel will look like this. Let's do, well, we could do the full case, I guess. Suppose we have the full case. So we'll have y1 equals h1x plus z1. y2 is h2x plus z2. In most, usually these all have a different number of antennas, right? So suppose usually we say that this is n1 antennas. So n1 dimension n1. So that's a length n1 vector, length in the sense of dimension. This is length dimension n2. and this will be dimension m. So m transmit antennas. So we can call this an m by n1 by n2 broadcast channel, vector broadcast channel, right? M transmit antennas, n1 receive antennas at terminal 1, and 2 receive antennas at terminal 2. So h1 is an n1 by m matrix, h2 is an n2 times m matrix, and these z's of course have the same dimensions as their corresponding y's. Okay, so that's the vector channel. Looks already quite a lot more sophisticated, but it's just a broadcast channel, right? Turns out it's not degraded in general. So a common case that's studied is, for example, N1 is 1, N2 is 1, because most of your cell phones, they do have 2 antennas, but they're only using one of them at a time, right? One is usually vertical, horizontal, depending on how you're angling your hands and your head and the interference. But so usually we look at m times 1 times 1, and the most commonly studied case that's already very interesting is 2 by 1 by 1. Then these are scalars, that's nice, and these are vectors. Okay, but let me just write out the general case for the moment. So we could now do everything we've done up to now. We could use, we could choose, well, time sharing. Okay, so how does time sharing work? Well, then we just have point-to-point MIMO channels twice, right? So we could, using time sharing, maybe we can draw this. Let's suppose we just have R1 and R2, so 2 separate rates. Then what's the capacity to channel 1? Well, this is my channel. I'm assuming here H1 is known to everyone, so I have to do a singular value decomposition of H, and then I do water filling on the singular values, and I get some, whatever that rate is. So I'll get some rate here. Similarly, I can do that for user 2, and then I can just time share between the two. So that's one approach, right? So it's time sharing. The idea here is SVD, singular value decomposition, and water filling. And time sharing. And as you might guess, I can also now do time sharing with different power levels or on 2 time slots, and then I can get a bigger rate, right? So I can do a more sophisticated time sharing, which might get rates like this. It's interesting to think about, right? So it's not quite so simple, right? Already there, it's not so simple. So in other words, there's more you can do with time sharing for vector broadcast channels too. That's what's commonly done in practice, of course, is you could optimize these things, but usually it's not done, usually it's not so much done in this way, but okay, it's one way of doing it. It's still orthogonal signaling. You optimize the power levels at different times, so you can do this power optimization. Fine, so let's do the second method. Well, we could use superposition coding. And I mentioned one way of doing superposition coding is to, for instance, suppose we have very low noise on this channel, then maybe we should be doing coding to get rid of interference. That will give us the best capacity scaling anyway. So one way, usually we use, so that's one way of thinking, one way of doing superposition is through linear precoding. So what we do is we just stack these 2 vectors into a big Y, right? So we can stack Y1, Y2 to get a Y. So that way we're stacking the H matrices into a bigger matrix, and X goes across both anyway, and then we get the stacking of the noise. And now it looks like a point-to-point channel, and what you can choose for X is statistics to do a pseudo-inverse of this, for example. So if this was length 2, if it was scalar, these would be 2 vectors, this would be a 2 by 2 matrix. This is length 2 vectors, so we could use a precoder that inverts the channel, or that does an MMSE inversion, or that does a singular value decomposition kind of operation followed by sophisticated coding and so on, right? So there's a lot of options I can do to do superposition coding here, and that's what's done in practice usually. The most common practical, if you open up most papers that deal with these channels for in the IEEE transactions on communications, that's what's used. And most people use pre-coding, which is just the pseudo-inverse. Well, I don't know. Let's just call it this. So x is just going to be the pseudo-inverse of this. I'll just call that h dagger times some pre-coding value x tilde, let's say, right? And this will affect, and if you can invert this, you would actually fully invert it and get two independent channels, right? That's the most common approach out there right now. Works very well for most fading statistics, but it's not optimal, but it works quite well. So you might get, rates that look like this. If the channel is orthogonal, we would even get this, rates that look like this, potentially. Okay, so you might get something better. Now it turns out the most interesting method, also the one that's most difficult to implement, but turns out to be capacity achieving, is Martin coding for this problem. Something completely non-obvious at that time because no one really knew about Martin coding in the communications literature. It was a pure information theoretic object. And it was only, again, I'm mentioning it was only rediscovered, this dirty paper coding concept, around 2003. And then it took several years to prove that this was actually the capacity achieving method. So what I'd like to do is talk about Martin coding again. Okay, so let's talk about Martin coding for this problem. And you remember what it looks like. So what we have to do now is the following. What's the Martin region? Well, remember what we had? We had R1 less than I U1 Y1, R2 less than I U2 Y2. I guess I shouldn't have erased what I just erased because I'm just going to write it again. So this turns out to give the capacity minus I U1 U2. However, remember how we can get to capacity? We can go at either corner point and then timeshare. So let's do that. Let's go to the corner points. Well, what are the corner points? There's two of them. There's either this one with R2 less than I of U2 Y2 minus I of U1 Y1 U2 Y2, or the other way around. Right? And maybe I want to do the one the other way around because I think I want to match it to that problem we just looked at. So let's just do it the other way around. R1 less than I of U1 Y1 minus I U1 U2. So there's two orders. And now, of course, these are all vectors, right? So Y is a vector, Y1. Oh, this is blue again. Y1, Y2. And it's natural to expect we should choose the u's to be vectors. In fact, the u vectors will have the same dimensions as x. Okay, it's not obvious, right, that this is the right thing. Maybe u's could be bigger, right, bigger vectors. There's no reason to believe they're not. But the natural approach is just to choose these as all vectors. And now we have to choose some joint distribution between u1 and u2, and then some function to map u1 and u2 to x. But the natural approach is just to use the Gelfand-Pinsker structure I showed you. Remember what that structure was? It looked like this. We first encode w2 to u2, and then we treat this u2 sequence as state. It's now a complicated state. It's a sequence of vector states. Then we use a Gelfand-Pinsker coding to get rid of the interference completely, which we know we can do also for vector channels. So this is where the W1 comes in. This is the state. This is the W1. Then here's what I'm labeling as my X1. I'll come back to that in a moment. And then we'll add these up to get my X. Just that I have to be a little careful. Do we twist this in any way? No. So it's just a pure addition. Like, because they're vectors, it could have been that I rotated them somehow, but I don't. Okay. So that is the architecture. And now I'll rewrite this again in not blue, but we'll look at what it is. The U2 vector is also going to be Gaussian, zero mean as a vector, but with a covariance matrix. And the right covariance matrix to choose is, well, we'll just choose it general, and then we'll have to optimize it. So that's like choosing that alpha p. So this just becomes q u2. So we'll have to optimize over that covariance matrix. That by itself isn't so trivial to do, because we already see it shouldn't be trivial to do, right? Here we're also having complicated things to do just for point-to-point channels, singular value decomposition and water filling. So it's clear, even here it's a numerical optimization. So for sure we should expect already here, this should be numerical too. And it's interesting to come up with algorithms to do that numerical optimization, because those aren't obvious either, right? So there's a lot of fun stuff happening in this problem. Anyway, we get this, then we'll choose x. 1 to also be a vector, 0 mean as a vector, and this will also be general, qx, this will be our qx1, independent, so these two are going to be independent. These we choose to be independent, just like for the scalar case, and then we'll choose our u1 vector to be just similar kind of thing, x1. And now rather than beta, we need a rotation matrix that we also have to optimize, plus b u2. And it turns out that the right choice for b gives us a certain, or it's based on the MMSE decoding or the orthogonality principle. So b is an MMSE matrix. And I'll just write it all out. qx1 h1t. You'll see it has an MMSE shape. Here we have qz1, that's the covariance matrix of the noise. Then we get plus h1, qx1, h1t, that's that h1 minus 1. Okay, so you see it has this kind of MMSE shape. Here's the covariance matrix of some channel output, and this is the expectation of something and something that we're using to estimate. So this is an MMSE matrix here, and that MMSE matrix ensures us orthogonality principle to get certain independence. And then the final thing is just to choose this as the sum, like I've already shown you. Okay, and with that choice, we can compute these, and we get the following rate region that has the following form. And then we'll plot this. It's a little bit longer. Well, I think I can fit it in. So it turns out that the second one, R2, will become, this side here, will become 1/2 the logarithm of the determinant of the covariance matrix of Z2, that always has to appear, plus H2 qx1 plus qu2. Both of these we still have to optimize, h2 transpose, divided by the determinant of the interference. So this is the interference plus noise now, qz2. So here's the noise, right? This is power. This is the signal to interference noise ratio, h2 qx1 h2 transpose. So if we look at that just quickly, notice this is the noise and this is the interference. Why is this interference? It's the x1 going through h2, right? Because x1 is something internal here that is carrying the information for user 1, but it's also going through h2, so it interferes, right? And then r1 turns out to be much simpler. This expression will just be the interference-free rate, right? We know that this will just become a half of log of just the capacity of the other channel. So this one turns out to be just 1/2 log determinant of just a signal to noise ratio, qz1 plus h1 qx1 h1t. So that's the divided by the determinant of qz2. Right, so here we have signal to interference plus noise ratio, here we have signal to interference ratio. And if we plot, if we now vary, so what we can vary here are these parameters here. This is left to optimize, and so is this. And you can see it already looks pretty ugly because we have this qx1 in both the numerator and denominator in a positive and a negative logarithmic part. So it's not obvious how to do this optimization. If we plot, and I'll say a few words about that in just a second. because that was simplified strongly in around 2005, that optimization, using the duality of broadcast channels and multiple access channels. So it was an important paper and result from the Stanford group that made this optimization simple. The duality was the main purpose of the duality is to simplify this optimization. But so if we plot this, what will we get? We'll get a very large rate 1. If we now optimize over these curves, you'll see curves that look like this. They go out steep here and then come in slow here, which should make some sense. I'll try to draw it in a way that I want it to come down and then stay out. Okay, so they're very good here because there's no interference for user 1, but they come in kind of slow here because of the interference. Okay, and now if we do it the other way around, guess what's going to happen? The same kind of curve, just the other way around. So what we're going to get is another curve that goes out steep here and comes in slow here. And guess how we can improve this? So we get a union of these 2 points, but then we can also timeshare across the top points. So we can also operate here part of the time, here part of the time, so that our best region will just be here, a straight line between these 2 points, right? And the white curve, right? So this part here is due to timesharing. This here is the timesharing points, and right now we can only achieve these points through timesharing. And this here is without timesharing. This is with timesharing these 2 points. And these curves here are either doing Gelfand-Pinsker one way or Gelfand-Pinsker the other way. And that's the capacity region. Okay, not obvious at all, right? I mean, why that would have a shape like this and that you would get a flat piece here. But that turns out to be true. So there are outer bounds that were developed to prove that. And this was, again, it was a sort of, it took several years. It started around 2002. Then there was a lot, you know, especially a lot of PhD students. There was a PhD student, I guess it was basically Pramod Viswanath at Berkeley was working on this. He was a PhD student of David Che, and you had Sriram and Nihar, and then you had Wei Yu, who's now at University of Toronto, was also a PhD student with Chofi at two Stanford groups, one Berkeley group, all, you know, around Silicon Valley. They're all competing with each other to solve this problem. The first problem that was solved was finding the sum rate was found first. And then it took several more years to establish that, you know, this Martin coding was optimal for these points too. And then finally the full version with the common rate too was only very recently solved, right? Maybe 3 years ago by Chandra Nair and his student Geng, and I think Geng is the name. Okay, so you do have to use, to get all these points, you have to use the Gelfand-Pinsker 2 ways. But it turns out, interestingly, that Martin coding is optimal without a common rate for wireless base stations, right? If we can use Gaussian modulation, right, which we can't, so we have to have QAM, right, and so on. Is it still optimal then? I don't know. I don't know if anyone's actually proved that. It's not as easy to solve now anymore. Right? You'd have to use shaping on 16 QAM and all that and still try to prove an outer bound that matches. I don't think anyone's ever done that. So this is all for but the Gaussian modulation is good enough because usually you try to approach that anyway. Right? So, but you need to use Martin coding. If we used superposition coding, we get rates below this. Okay, we don't. But for many practical problems, you can approach it quite closely. So for example, if the SNR is very high, then coding, like for deterministic channels, is pretty good. And usually nobody ever builds Martin coding today. It's just too complicated because no one knows how to build all this stuff in a good way, right? And even how to do coding for that. I mean, how do you build the encoder? How do you build the decoders and so on? It's easy to write out the equations, but then it's hard to actually build devices that approach this performance. Okay. Yes? I think I said everything I wanted to say. Like I said, we still have to optimize. In this form, it's hard to tell how to do the optimization. The optimization comes simpler in the dual perspective, so when we get to duality, we'll talk about that again for the vector multiple access channel. There's still, you could do a lot of stuff here. It's quite sophisticated. I'm not going to do much more on that here. And that's probably a good time to stop. So tomorrow